Okay, let's start. Good morning, everyone. This is the fourth and the last ESTP webinar about introduction to big data. And I'm Donato Summa. I'm a computer scientist, and I've been working for 7 years for the Italian National Institute of Statistics. And at the moment, I'm involved in big data projects within my institute and into the ESSNet Big Data project. Just a few words before beginning the real lesson. Just a few words about ESTP courses. This kind of courses provide European statisticians with continuous training in new methods, techniques, and best practices, and cover the specific needs of the European statistician working in national statistical offices of the European Union. Employees of national statistical institutes or other national authorities of European Union, EFTA countries, Eurostat, as well as candidate and potential candidate countries can participate to ESTP courses. In this lesson, in today's lesson, as you probably can see from the slide, I'm going to introduce the main concepts about distributed systems and distributed computing that will be useful to better understand the next topics of the presentation that are Hadoop, the Hadoop framework, and the related components. So we will see basically HDFS module of Hadoop, MapReduce, and then we will have a look at the main Hadoop related projects that are Pig, Hive, and Spark. Just at the end of this lesson, we will have a very briefly look to the trusted smart statistics concept and the European Union big data test infrastructures. But let's begin with the first topic of this lesson, principles of distributed computing. Now, in order to understand what distributed computing is and how it works, it's necessary, first of all, to understand what is a distributed system. So, what is a distributed system? Well, in this slide, I wrote down a very short definition that could be useful to better understand, to better memorize what we are talking of. A distributed system basically is a collection of separate and independent software or hardware components called nodes. The nodes are basically computers, and these computers are linked together by means of a network and work together coherently by coordinating and communicating through message passing or events to fulfill one end goal. So as you can see in the slide, we have a situation within which we have several machines, several computers in a network, and they work together by passing messages over the network. And at the end of their job, at the end of their collaboration and cooperation, they provide a result. Now, it's important to say that the nodes of the system, the nodes of the distributed system, the computers within the network, could be unstructured or highly structured, depending on the system requirements. But in any case, the complexities of the system, the number of nodes, their structures, how they are linked together, and how they work together, all this detail remain hidden to the end user, human or computer, and the whole system appears as a single computer. So if you, as an user, um, if you send requests to the distributed system, you have the feeling to interact with just a single computer and not with a collection of computers. This is very, very important. Okay, now there's another concept to be clarified. Nearly all existing large distributed systems, especially modern ones, are overlaying networks. What is an overlaying network? An overlaying network is a virtual network built on top of an existing physical network. So basically, we have a group, a collection of computers that are on a network, for example, on the internet network. But just a subgroup of computers form a so-called overlay network. An example of an overlay network is the BitTorrent. So, for example, when you use the BitTorrent protocol by downloading and installing BitTorrent clients, well, you are using a distributed system, and in particular, you are relying on an overlay network, the BitTorrent overlaying network. Okay, so let's move on and let's talk a little bit about the main characteristics of a distributed system that I resumed in this slide. Basically, we will talk about no shared clock, no shared memory, concurrency, and heterogeneity. And let's start with the first characteristic, the no shared clock. No shared clock means that each node in the distributed system has its own notion of time. So, for example, if you ask to one computer in the system, what time is it? Maybe the answer could be 3 in the afternoon. If you ask the same question to another computer, maybe the answer can be different because the first computer could be physically located, let's say, in New York. The second computer could be physically located in Rome, and so on. We can say that harmony is achieved through coordination and synchronization in these cases. Another concept, another characteristic of distributed system is the so-called no shared memory. This means that the state of the program is distributed through the system. So we don't have a common area, a common memory accessible by all the nodes, by all the computers, but each node in the system, each computer of the distributed system has its own memory. That's why we are talking about no shared memory. The third characteristic that I want to point out is the concurrency. Concurrency means that processes, programs, let's say, are autonomous and execute tasks concurrently. Concurrently just means in overlapping time periods. So, for example, in this slide, we can see that we have 5 tasks and they are executed at the same time. So we have overlapping time periods of execution. The last characteristic that I want to point out is heterogeneity. This means that each node in the system, into the distributed system, could have different hardware and software configuration. So, for example, we can put together and we can make work together several machines with several different operating systems smoothly. The last, the very, sorry, okay. In terms of scale, it's possible to identify 2 basic types of distributed system, the so-called clusters and the so-called grids. What's the difference? Okay, a computer cluster is a local network of 2 or more homogeneous computers. So a computation process on such a computer network is called cluster computing. In the second case, grid computing, well, grid computing can be defined as a network of homogeneous or heterogeneous computers working together over a long distance to perform a task. So basically, differences are the fact that in one case, we are talking usually about a local network. In the second case, we are talking about long distances. In the first case, we are talking about homogeneous computers, usually. In the second case, the computers, the nodes of the network can be homogeneous or heterogeneous. So that's the main, these are the main differences between a cluster and a grid. Now, the distributed computing is a type of computing over distributed systems. We talked about distributed systems so far, so now we can talk about distributed computing. Distributed computing is concerned with building and establishing computing models for distributed systems and working out algorithms to solve problems. Cloud computing is a good example of distributed computing over a distributed system. Now, before moving on and before being able to explain Hadoop and its components and its modules, let's see the main concepts related to the distributed computing world. And one by one, I will explain all of these concepts. So let's start with the first concept, the node concept. What's a node in a distributed system and therefore within distributed computing? A node is a software or hardware component that has its own processor and memory and is able to communicate with the rest of the system. Basically, a node is a computer in a network. Node can form groups, and the groups can be divided into open groups within which you can always add new nodes, and closed groups within which the number of nodes is prefixed. Okay, this was the first distributed computing concept. The second concept is the concept of resource. A resource is an asset that is accessed remotely by nodes. It could be anything that a node can take advantage of. So, for example, a resource can be a file, a folder, a service, a storage platform, a network, and so on. The third concept that I want to point out about distributed computing is the so-called distribution transparency. Distribution transparency means that everything that happens under the hood should stay invisible to the end users of the system. So, for example, you are not supposed to be aware of the resource locations. For example, the physical locations of the nodes into the distributed system. You are not supposed to be aware if a node crashes, or how the resources are duplicated into the system. All this stuff is called distribution transparency. And another very important concept related to distributed computing and distributed systems is the so-called middleware. A middleware is a logical layer that connects nodes and make them appear as one single supercomputer. It's a sort of, let's say, operating system that is responsible of managing resources, communication, security, failures, and so on. So, for example, as you can see from the slide, we can have several client applications that wants to request services to our distributed system. They do not interact directly with a node of the system, but they interact with the middleware. Then the middleware is responsible to interact with the nodes of the system and to collect the result in order to provide it to the final user, let's say to the final client applications. Okay. Another concept is the concurrency. We already talked about concurrency when I was talking about the main characteristic of a distributed system. In this case, I just want to add that within a distributed system, when we are doing distributed computing, multiple operations and tasks are performed at the same time, but they are not isolated. They can cooperate. So, for example, in the phase one, the task number one and the task number two are cooperating. In the phase two, task number four and task number five are cooperating, and so on. Okay, let's move on with another concept of distributed computing, the coordination and the synchronization. These two features ensure the smooth collaboration between operations and activities tackling the problems of no shared clock between processes and solving the problem of data corruption and inconsistency if two entities try to access data at the same time. I don't want to enter into details of this stuff. So let's move on with the next concept, the last one about distributed computing that I want to point out, the architectural model. The architectural model defines the structure of the system. So, for example, how nodes are arranged and how nodes communicate and interact. It provides better management of the complexities and easy of maintenance. The architectural model is mainly needed for software components due to the fact that the vast majority of distributed systems are overlay networks. And we can have different architectural model put in place. The most common architectures adopted are the client server, the three-tier, the n-tier, and the peer-to-peer. So let's see briefly what is the client server model and the client server architecture. Well, it's very easy to explain what is the client server architectural model. Basically, it's what we all do every day when we request, for example, a web page from our browser. So from an architectural point of view, we have different clients, let's say computers, people, laptops, smartphones, etc., that request services, resources to a server. And in order to make these requests, they use the network, internet usually. So a client sends a request via internet to a server, and the server is responsible to provide the requested resource to the clients. That's the client-server model. Now, the three-tier architectural model basically is just a more sophisticated client server. This means that, for example, the clients send the requests to a server, and the server or the servers that are responsible to provide resources do not provide resources directly, but in order to provide the final result to the client, they also have to interact with other servers, with other nodes of the distributed system. So, for example, with a database server. And by extension, we can also understand how entire architectural model works. Basically, we can define an entire architectural model as an even more sophisticated client-server model. We have different layer of nodes, different layers of servers that have to cooperate before being able to provide the final result to the client. The last architectural model that I want to present is the so-called peer-to-peer architectural model. In this model, all the nodes can be both clients and servers. So there's no distinction between the roles. A typical example of a peer-to-peer architectural model um, is the peer-to-peer networks. So, for example, if you want to download something from internet, you could use, for example, your browser, but if you are interested in a particular kind of resources, sometimes, let's say, illegal resources, films, uh, movies, songs, you have to rely on particular softwares like, for example, BitTorrent or Torrent in general. And when you download, install, and execute your client, your BitTorrent client on your computer, basically you are one of the nodes of the peer-to-peer network, of the peer-to-peer architecture. Okay, it should be clear what a peer-to-peer architectural model is. So let's talk about the another concept of distributed computing, the so-called global state. What's a global state? The global state is the union of the states of separate processes. So a global state is a sort of a global view of the system that describes its properties at a particular point in time. As I told you before, usually in a distributed system, we have several nodes, and each node is independent. This means that it has his own memory. So the global state could be seen as the sum of each individual memory state of each nodes in the system. Okay, now let's talk about the advantages that we can benefit, that we can have if we decide to use a distributed system and we put in place distributed computing. In a nutshell, I summarized the main advantages that we can have in this slide. So basically, the main advantages are the so-called fault tolerance, a very high price performance ratio, scalability, resource sharing, and standards. Let's talk a little bit in more details about fault tolerance. Fault tolerance means that if one of the nodes in the distributed system for some reason crashes, well, our computation can go on because all the stuff that was in charge of the machine that crashes can be, how can I say, can be done by the other machines, by the other computers in the network. They can do the work of the computer that crashed. Of course, the performance will slow down a little bit, but the advantage is that we don't have to start from the beginning what we were doing. And this is a very big advantage in comparison with the traditional computing model. With the traditional computing model, basically we have just one computer, and if on that computer something goes wrong, the computation stops. within a distributed computing model, within a distributed system, if something goes wrong on a single computer, the computation goes on. The second advantage of distributed computing is the price-performance ratio. So we can say that it could be very, very expensive to buy a single machine, a single very powerful machine, in comparison to buying several low-profile machines that put together can reach the same performance of the previous one single costly machine. So basically, how we will see in the in this lesson, Hadoop is heavily based on this advantage, because what we will see in Hadoop will be the collection of several computers, also commodity hardwares, that put together can reach a very good computational power. And another advantage is the so-called scalability. Scalability means that we can always add new nodes to our system in case of needs. If we need more power, we can always add other machines to our system. And this is working, and this works also in the other sense. I mean, if we have a system with, let's say, 12 machines, and for some reason we need no more all the computational power, we can also decrease dynamically the number of computers of our distributed system. So we can increase or decrease the power of the system by adding or removing machines from the system. And this is called scalability. Another advantage is the resource sharing. So, for example, if we need for a particular project a resource, a very specific resource, such as a very powerful GPU, graphic processing unit, and we don't have it on our computer, we can benefit of this resource that could be hosted on another node of the system. And this also is valid for other kind of resources. So, for example, databases or particular softwares and so on. And last but not least, we can also benefit from the adoption of standards. The adoption of standards makes possible to put together different machines, different computers having different hardware or software configuration. So, for example, we can make a system within which we have computers with different operating systems, and this won't be an issue. Okay, but all of the advantages that I've just explained do not come for free. Of course, there are also disadvantages, let's say, issues that we have to deal with. And in particular, we have to deal with the complexity of distributed systems, distributed computing. Complexity means that we have to sort out issues, problems related to node interconnections, failure detections, possible inconsistencies among nodes, software development, because as you probably know, it's very different to develop a software for one single computer and the same software for a distributed uh, computing model and other stuff. So we have to deal with all of these complexity if we want to use a distributed computing model and if we want to benefit from the advantages that I explained so far. The second cons is the security. Due to the fact that we have independent computers in the system, each computer could have a different security level. So, for example, on one computer, maybe the antivirus could not be updated, or maybe the firewall is not working properly. And that this is, of course, a security issue that we have to take into account. So basically, we have to deal with the fact that we have independent computers and we can't directly control each one of the nodes. The second issue that we have to deal with, talking about security, is the message passing mechanism. In order to work together and to reach the final goal, the nodes of the system have to communicate. And in order to communicate, usually they pass messages over the network. And of course, a message could be intercepted by others, unauthorized people. And this is another issue that we have to deal with. Okay, that's enough for the security stuff. And of course, last but not least, if we want to use a distributed system, we also have to deal with the management of this complex system. So we have to deal with the fact that we usually have different operating systems installed on our nodes. The nodes could have different hardware configuration. We have to deal with the network that is used to connect the nodes, the security, as I talked before, and so on. So now that you should have a general idea of what a distributed system is and how distributed computing works, let's provide some examples of distributed systems and applications. Example of distributed systems and application could be, for example, the communication networks, internet, for example. It's the best possible example of a distributed system, but also phone networks, mobile networks, and so on. All the network applications, such as the www protocol, the peer-to-peer networks, the distributed file systems, distributed databases, all the real-time systems such as air traffic control, all the bank transactions, all the booking systems, and of course also the so-called parallel computing that is used when we need to do some very specific work, such as scientific calculation or cluster or grid computing, computer graphic imagery rendering. So, for example, when you go to the cinema and you watch a computer graphic movie, you have to know that all the work behind that movie was done over a distributed system and by using distributed computing. Okay, now we are ready to talk about Hadoop. Hadoop and its components. The first question is, what is Hadoop? The Apache Hadoop open source software library is basically a framework, an infrastructure that allows for the distributed processing of large data sets, big data, let's say, across clusters of computers using simple programming models. So is basically the software that we will use if we want to benefit from a distributed system. Apache Hadoop is designed to scale up from single servers to thousands of machines, and we can also use commodity hardware. So, for example, old computers. And each of these computers offers local computation and storage. So, as I told you before, each node into the distributed system is basically independent. That's why it can offer local computation and storage. The library, the Apache Hadoop library itself, is designed to detect and handle failures at the application layer rather than rely on hardware to deliver high availability. So basically, we are talking about the middleware layer of Apache Hadoop that is responsible to guarantee high availability. Now, the Hadoop project, includes the following modules. We have the so-called Hadoop Common module, and within this module, we can find all the utilities that support the other Hadoop modules. We have the HDFS, the Hadoop Distributed File System. This is a very, very important module of Hadoop with Hadoop MapReduce. And we will have the opportunity to talk a little bit about HDFS in MapReduce later on in this lesson. Okay, these are the main Hadoop modules, but there are also Hadoop related Apache projects that can be used on top of Hadoop. And in particular, in this lesson, we will see Apache Spark, Apache Hive, and Apache Pig. And in this slide, you can see the whole Hadoop ecosystem. I just put circles around the modules that we will see in this presentation, but you have to understand that the Hadoop ecosystem is very wide and very complex. So it's not enough one single lesson to explain everything. I try to do my best in order to provide you a good understanding of the main modules of Hadoop, HDFS, and MapReduce, and I'll try also to do my best in order to introduce you uh, three very common Hadoop related projects by Apache. But let's start with the main components of Apache Hadoop, Hadoop HDFS and Hadoop MapReduce. Let's start with HDFS. Now, HDFS is an acronym and means Hadoop Distributed File System. Before being able to fully understand how HDFS works, let's spend a few words on how a generic distributed file system is and how it works. So in this slide, you can see on the left side a traditional file system, the so-called local file system. Basically, we have just one computer with one storage device inside it. Let's say that it has the capacity of 1 terabyte. On the other hand, on the right side of the slide, we have an example of distributed file system. In a distributed file system, we have several computers, each one having its own storage facilities. And if we sum up all the storage, we have basically from a virtual point of view, one single machine with a storage that is the sum of all the storage of the machines of the computers that are in the distributed system. Now, when we put our data into a distributed file system, it means that data are no more located on a single machine, but they are distributed over several machines. And the user that interact with the system, with the distributed system, from any node of the cluster, will have the feeling, the sensation to deal with a traditional local system. So a distributed file system abstracts the real data distribution over the nodes and makes transparent to the user this organization. But why is it convenient this way of arranging data? Why is it convenient to use distributed file systems? Well, there are limits about the amount of data that a single computer can store or can manage. So, for example, you can't store on a single computer a very huge amount of data. Let's say, for example, 100 terabytes. It's impossible to store them on a single computer. And even though there were no limits about the storage capabilities, it would take too much time to process a huge amount of data on a single machine. So, for example, let's assume that that 1 terabyte of data will cost you 1 hour of execution time. If we want to process 4 terabytes of data, you will need 4 hours into the traditional way of doing things. In comparison, if you use a distributed file system, you can split the data over several machines, and at the end, the time that you need for elaboration purposes, it's reduced because the execution on the data is a parallel execution. So if you want to process a very huge amount of data, you can reduce the execution time just by splitting the data over several machines of a distributed system. Okay, now that we have a general idea of distributed file system, it's the right moment to talk about HDFS, a particular distributed file system, the Hadoop distributed file system. HDFS is the data part of Hadoop. It has files and folders, as usual in every file system, and can store petabytes of data. In HDFS, we have basically two kinds of nodes: name nodes and data nodes. The name node, also called master node, is the node or the nodes that are responsible to run the so-called master daemon. The master daemon is basically a program, a process running into the background of the computer of the master node, and it manages the data nodes and the metadata. So basically, the master node is responsible of know how the data are arranged over the slave nodes. In contrast, the slave nodes, also called data nodes, are nodes that physically store data and serve data reading and data writing requests that are sent to the distributed system. Now, each file is saved in the Hadoop file system, split in blocks of a prefixed size that are distributed among the data nodes by the name node. So, for example, if we have one file of 380 megabytes, it will be split into 3 blocks. The first 2 blocks will be 128 megabytes, and the last one, the remaining part of the weight of our original file. So now that we have split the original file in blocks, we have to distribute the blocks over our data nodes, and this operation is made by the master node. So retrieving a big file from HDFS, so for example, retrieving the file that we saw in the previous slide, means to retrieve all the blocks belonging to that file from the nodes that store that blocks. Now, if a data node containing one of the blocks we are interested in crashes, it will be, of course, impossible to retrieve the entire file, and this is clearly unacceptable. The solution to this problem is the replication and distribution of data among different data nodes. And by default, a block is replicated 3 times. So how can we can see what is going on in this slide. We have the previous file, and the previous file was split into blocks. The blocks were distributed over the data nodes. And let's assume that now we want to retrieve the file that we put into the Hadoop distributed file system. Let's assume that one of the data nodes for some reason crashes. It's still possible to retrieve all the blocks related to our file because, for example, the blue block is available from the machine, let's say number 1, and from the last one. The red block is still available from the second and from the third machine. So if something goes wrong, if a data node goes down, it will be still possible to retrieve all the data that we stored into our distributed file system, because it's really improbable that 3 nodes by default crash simultaneously. That's the idea behind the Hadoop distributed file system. Okay, so it's time to talk about MapReduce. MapReduce is the Hadoop component in charge of parallel processing the data stored in HDFS. We saw HDFS, that is the storage part. Now we are going to see the MapReduce, that is the processing part of the system. As you can see, MapReduce relies on 2 basic functions, the map function and the reduce function. That's why it's called MapReduce. MapReduce is a large-scale distributed model, is a parallel programming model, and is used for analytics purposes, is used in recommendation systems, in classification systems, and when we need to index and search data that we previously stored. In particular, MapReduce is an algorithm, a way of doing things, and is implemented in Apache Hadoop and used by several Apache Hadoop components such as HDFS that we already talked about, Pig, Hive, and HBase. The main advantages of MapReduce are the parallel processing of data that reduces the execution time considerably, and the data locality principles that avoids the transfer of data over the network. So basically, we are bringing processing to data instead of bringing data to processing. And in this slide, you can see the same example that I've already showed in previous slide. So basically, we are combining the capabilities of HDFS. So we are splitting a huge file, not very huge in this case, into blocks. We are distributing blocks over several nodes, and each node is responsible of processing its data. So at the end, due to the fact that the processing acts in parallel, we have a reduction of execution time. That's the spirit. But let's see some details about the MapReduce way of doing things. So at the beginning, we can say that a client requests a computation on a dataset to the our Hadoop cluster. So the middleware is responsible to redirect this request to the master node. The master node detects the slave nodes containing the files or the blocks of interest of interest. Let's say the files or the blocks of the data sets we want to operate on, and starts the computation on them, keeping track of the progresses. So for example, the dataset was split, was divided among several slave nodes, the slave node that have a square in the picture, and this slave node start the execution on the data that they have locally stored. In the meanwhile, the master node is keeping track of the progresses, and this is called the map phase. Then, when the computation ends, the master node instructs some slave nodes to put together all the partial results and produces the final result. The slave nodes responsible to put together the partial results can be the same slave nodes that operated on the data, but they can also be other slave nodes. This phase is called the reduce phase, when we have to put together all the partial results in order to obtain the final result. So the final stage is when the master node collects the final result and makes it available to the user. The final result could be, for example, a file or a data insert in a database or something else. More specifically, we don't have just the map phase and the reduce phase. There are also other, let's say, small phases in the middle. It's not really so important at the moment to explain all the details of the different phases, because my objective is to provide you a general idea of what is going on and what are the main phases of the process. So I think that we can more or less skip this slide and start talking about Pig. Apache Pig at the beginning, well, Apache Pig, of course, is a component, an Apache Software Foundation program related to Apache Hadoop. It's not part of the Hadoop core, but is something that can be used in conjunction with Hadoop. Before explaining what Apache Pig is, it's important to spend some words about the motivations that triggered Apache Pig. We can say that at the beginning, programs were written only on MapReduce using Java. So if you wanted to benefit uh, from the Apache Hadoop, you were forced to write distributed programs in Java, and you were forced to respect and to implement the MapReduce modeling programming model. So developers had to mind the map, sort, shuffle, and reduce fundamentals while creating a program for which they needed common operations such as joining, filtering, and so on. So basically, they had to find out a way to implement joining operations, filtering operation in a map reduce fashion. And the challenge was to keep building up while maintaining, optimizing, and extending the code following a rigid data flow, the data flow enforced by MapReduce. So consequently, the production time increased. That's why someone decided to develop another solution for this problem, and in particular Apache Pig. Apache Pig was developed in late 2006 by Yahoo researchers to overcome the MapReduce issues, and later on in 2007 it became an Apache open source project. So basically, Apache Pig provides an alternative to Java and to the MapReduce pattern of programming. Apache Pig is extensible, self-optimizing, this is very important, and easy to program. It uses both structured and unstructured data as input to perform analytics, and uses HDFS to store the results. So that's why it could be used jointly with Hadoop, because it behind the scenes relies on MapReduce, and it uses HDFS to store data. So in a nutshell, Pig is a scripting platform that runs on Hadoop clusters designed to process and analyze large datasets. There are two major components of Pig: the Pig Latin script language and the runtime engine. Let's talk about the first component, the Pig Latin script language. It's a procedural data flow language that abstracts the programming from the Java MapReduce idiom into a notation which makes MapReduce programming high level. So it will be a sort of SQL for relational database management systems. Pig Latin contains syntax and commands that can be applied to implement business logic. So, for example, we will have the load command, the store command, and so on. And this script language, the Pig Latin script language, can be extended using user-defined functions, the so-called UDFs, which can be written not only in Java, but also in Python or in JavaScript or in Ruby or Groovy. And these user-defined functions can be called directly from the language. So you can benefit of them within the scripts that you have to prepare when you want to execute operations on the data. Okay, the second component, the second main component of Pig is the so-called Pig runtime engine. The Pig runtime engine is a compiler that produces sequences of MapReduce programs. It uses HDFS to store and retrieve data that we are interested in and that we want to use to work on. And it's used to interact with the Hadoop system. So basically, the Pig runtime engine parses, validates, and compiles the script operations written in Pig Latin script language into a sequence of MapReduce jobs. We can see the Pig runtime engine as a sort of, let's say, converter. You can write your script in a very handy programming style. You can write your script with Pig Latin, and then the Pig runtime converts what you've written, what you wrote, into a sequence of MapReduce operations. So basically, at the first step, you just have to write your script, and within your script, you have, for example, to load the data and write some operations such as joining, filtering, grouping, stuff like that. Once you have written your script, the Pig engine is responsible to parse and check the script. It optimizes the script, and it does a series of other kind of operations. At the end, it produces an execution plan. This execution plan can be directly executed by Hadoop and produces the desired results. So behind the scenes, what is going on, it's always the same. We have produced in a more convenient way MapReduce scripts, and these MapReduce scripts programs are executed by Hadoop on top of HDFS. So it's just a more convenient way to interact with Hadoop ecosystem. The main features of Pig are the following. You can have a step-by-step procedural control. You can operate directly over files. You can have the schema of the data dynamically assigned, and you can develop your own functions, the so-called UDF, user-defined function. You can use them within your script. And last but not least, Pig also provides support for many data types. Okay. Now, Pig can be executed in two modes. In the local mode or in a MapReduce mode. When you execute Pig in local mode, Pig relies on the local file system of your machine. So in this case, there's no need of Hadoop or HDFS. This means that you can use Pig also without Hadoop. But most common case, the most common mode of using Pig is the MapReduce mode. In this case, in this mode, Pig relies on HDFS and of course needs Hadoop. So in MapReduce mode, a MapReduce job is invoked in the backend. And in this case, what is going to happen is what I told you in the previous slides. Both in local and MapReduce mode, a Pig program can be executed in interactive mode. This means line by line in an interactive fashion, or a Pig program can also be executed in batch mode. So in this case, a file containing a script written in Pig is created and executed in batch. Okay, that's all for Pig. Now let's have a look at Hive, another project related to Hadoop. Apache Hive is a data warehouse software project built on top of Apache Hadoop for providing data query and analysis. It's mainly used to complement the Hadoop file system with its interface. And indeed, it provides a SQL-like interface to query data stored in various databases and file systems that integrate with Hadoop. Originally developed by Facebook, Hive is now maintained by the Apache Software Foundation and used by big companies such as Netflix and Amazon. Now, while traditional SQL queries must be implemented in the MapReduce Java API to execute SQL application inquiries over distributed data, Hive provides the necessary SQL abstraction to integrate SQL-like queries written in a particular language called HiveQL into the underlying Java without the need to implement queries in the lower level Java API. We can say that in this case, the main idea is exactly the same idea that was implemented in Pig. Due to the fact that is difficult, is annoying, is error prone to program in Java by following all the rules enforced by MapReduce, we are trying to find out alternatives. We saw the alternative provided by Pig, and in this case, we are seeing the alternative provided by Hive. Now, Hive, as I told you before, is a system to a program, it is a tool to interact with data warehouses. And since most data warehousing applications work with SQL-based querying languages, Hive in particular adds portability of SQL-based applications to Hadoop. That's the main objective of Hive. Now, let's spend a few words about the success that Hive reached so far. Hive reached a good success because normally organizations are accustomed to work with SQL on traditional data warehouses. But at the same time, when you have to deal with a very large amount of data, you are forced to use something like Hadoop. You cannot rely anymore on a traditional storage solutions, storage platforms. And if you have to use something like Hadoop, you have to learn how to use this Hadoop ecosystem. Learning how to use a new technology such like Hadoop can be an uphill task. So what you really need is a tool like Hive that provides SQL intellect so that users can write SQL-like queries in HQL, a SQL-like language, to extract the data from Hadoop, from the new platform, in the old fashion, in a SQL fashion. That's why Hive was so, and still is so popular and so very well received. So basically, the SQL-like queries, the HQL queries, are converted into MapReduce jobs by the Hive component, and that is how it talks to Hadoop ecosystem and HDFS file system. Also in this case, we are talking about a sort of an interpreter that avoids all the annoying tasks of writing directly Java programs following the MapReduce scheme. Common use cases of Hive. Well, Hive is commonly used when you have to do online analytical processing, when you have to deal with very large amount of data, and when you have to, how can I say, to interact with HDFS, but the only thing that you know is SQL. Instead, Hive cannot be used for online transactional processing and real-time updates or queries. Why? Because, of course, everything you write in Hive should be translated into MapReduce before being executed. So every time you need low latency data retrieval, Hive is not the right tool to use. If you want to reach that kind of performances, you have to use another tool, Spark, that will be the next topic of this presentation. But for the moment, let's resume what are the Hive main features. Well, Hive supports different file formats. It can store metadata in a traditional database. It has compression techniques. It provides HQL support. It's also possible to define user-defined functions, and it also has specialized joints and other specialized stuff that you can use when you have to interact, when you have to deal with data. Okay, so now the last very important topic of this presentation, Spark. The last tool, the last project that you can use and you can benefit of when you have to uh, deal with Hadoop. Has Hive and Pig. Also, Spark at the beginning was, let's say, a private project. In fact, it started in 2009 at Berkeley Laboratories. In 2010, it became an open source project under BSD license. In 2013 was given to Apache under Apache 2.0 license. In 2014, it became an Apache top-level project, and today it exists as a next generation real-time and batch processing framework. So this means, in a nutshell, that Spark is something that is really important. Both Spark and MapReduce are data processing frameworks in Hadoop. So if both of them basically are able to do the same things, which one should use and when? In order to compare Spark with MapReduce, it's first of all necessary to understand what batch and real-time processing mean. So, batch processing means that we have to deal with large amount of data or transactions that should be processed in a single run over a time period. Usually, the associated jobs run without any manual intervention, and the entire data is pre-selected and fed using command line parameters scripts. Batch processing is used to execute multiple operations, handle heavy data load, reporting, and generally speaking, offline data workflow. So, for example, if we need to create reports, weekly reports, daily reports, and the making of these reports requires several hours. Well, this is exactly the case of a batch processing. You can prepare your program, your script, you can launch it during the evening, and the very next morning, probably you will have the results ready because the execution took place during the night. And during the night, there was no manual intervention. That's the batch processing. Instead, the real-time processing of data means that the data processing takes place upon data entry or command received instantaneously. So it must execute on response time within stringent constraints. This means that you are in front of your computer and you write something, you press enter, and you expect to receive immediately the result. So we can also say that this is something that is interactive on the basis of what you write down. The system provides you the results. And real-time processing is something needed every time you want an immediate response. So, for example, if you want to detect a fraud in a system, this task could not be assigned to a batch job, because the batch job probably will be able to find out the fraud, but you will be aware of the fraud after a certain amount of time. In case of fraud, instead, you want to be immediately aware of what is going on in order to remedy the problem. Okay, so Spark was mm, triggered by the MapReduce limitations. I said that both Spark and MapReduce are processing framework. Spark, with respect to MapReduce, has the main advantage to being able to manage also, let's say, real-time execution. But let's see uh, in detail what are the other reasons, the other MapReduce limitations that triggered Spark. Well, first of all, MapReduce is unsuitable in real-time processing, because it takes normally minutes to execute jobs, depending upon the amount of data and the numbers of nodes in the cluster. Even for trivial operations, you have to wait 1 minute, 2 minutes, because of the overhead of the system and the phases of MapReduce algorithm. That's the first MapReduce limitation. The second limitation, as I told you before, is that MapReduce is unsuitable for trivial operations such as filtering operations, joining operations, because in this case you have to rewrite these operations in a MapReduce fashion, following the MapReduce pattern. From a conceptual point of view, a filtering operation is something that is very easy to be done. But if you have to implement the logic following the MapReduce pattern, trust me, it's not really trivial. It's not really easy. It's something annoying, boring, and error prone. The third MapReduce limitation is that MapReduce is unfit for large data on network, because it works on data locality principle. So you should avoid as much as possible to copy data over the network. Other reasons are that MapReduce is unsuitable with OLTP, because online transaction processing requires a large number of short transactions. As it works on the batch-oriented framework, MapReduce lacks latency of seconds or less. And when you have to do a transaction, you have to be quick, very quick. Moreover, MapReduce is not really suitable for processing graphs. To be honest, to be precise, if you have to deal with graphs and MapReduce, you could use Apache Giraffe library. But if you use this library, you are adding additional complexity on top of MapReduce that is complex on its own. And finally, MapReduce is unsuitable for iterative execution. Being a stateless execution, MapReduce does not fit with use cases like, for example, the k-means algorithm that need iterative execution. And for each step, you have to keep in memory what was happened into the previous step. Due to the fact that MapReduce is stateless, you can't do, you can't implement easily this kind of algorithms, stateful algorithms. So in order to address all these limitations, well, it was developed Apache Spark. Spark, technically speaking, is an open source cluster computing framework that addresses all the limitations of MapReduce that I explained so far. In particular, Spark is suitable for real-time processing, trivial operations, and processing large data on network. Sparks provides up to 100 times faster performance for a few applications with in-memory primitives as compared to the two-stage disk-based MapReduce paradigm of Hadoop. And Spark is also suitable for machine learning algorithms as it allows programs to load and query data repeatedly. How Spark can assure all this stuff? Well, because Spark has several components. The first component that I want briefly illustrate is the so-called Spark core. Spark core and RDDs, resilient distributed datasets, are the basis of Spark, and they provide basic input-output functionalities, distributed tasks dispatching, and scheduling. RDDs can be created by applying coarse-grained transformations on the existing RDDs or by referencing external datasets. Examples of these transformations are reduce, join, filter, and map. So the abstraction of RDDs is exposed through a language integrated API in Python, in Java, and Scala. As a result of the RDD abstraction, the complexity of programming is simplified, as the manner in which applications change RDDs is similar to changing local data collections. So again, you don't have to deal with the MapReduce pattern. You can use alternatives, more convenient alternatives in several languages, Python, Java, or Scala. The second Spark component is Spark SQL. Spark SQL or Spark SQL resides on the top of Spark core and introduces schema RDD, which is a new data abstraction and supports semi-structured and structured data schema. RDD can be manipulated in any of the provided domain-specific languages, such as Java, Scala, and Python by the Spark SQL. Spark also support SQL with Open Database Connectivity and Java Database Connectivity, commonly known as ODBC or JDBC. And this was the second Spark component. The third important Spark component is Spark Streaming. Spark Streaming leverages the fast scheduling capability of Spark Core for streaming analytics, ingest data in small batches, and performs RDDs transformations on them. With this design, the same application code set written for, let's say, batch analytics can be used directly on a single engine for streaming analytics. So, for example, if you want to deal with, let's say, Twitter posts, you can analyze, you can compute, you can do elaboration work on posts put on Twitter, and you can collect them in streaming, process them in streaming, and produce result in a streaming fashion with Spark Streaming, for example. Another component of Spark that is very used nowadays is Spark Machine Learning Library. This component lies on top of Spark and is a distributed machine learning framework. The machine learning library applies various common statistical and machine learning algorithms. With its memory-based architecture, it's 9 times faster than the Apache Mahout Hadoop disk-based version. Apache Mahout is, let's say, the equivalent project that you can use if you want to implement and execute machine learning algorithm with Hadoop. So it's basically an alternative to Spark machine learning library. The last component of Spark is GraphX. GraphX also lies, of course, on top of Spark and is a distributed graph processing framework. For the computation of graphs, it provides an API, an application programming interface, and an optimized runtime for the pre-GEL abstraction, a system for, let's say, large-scale graph processing. Okay, so we don't have so much time left. So briefly, let's explain the main advantages of Spark, and then we will move to the last two topics of this presentation. So for now, let's talk about Spark advantages. The first advantage of Spark is, of course, its speed. The second advantage is the Hadoop support. I want to say, and this is very important to understand, that Spark is Hadoop independent, but if required, Spark allows to create distributed datasets from any file stored in HDFS or any other supported storage system. The big advantage of Spark is the so-called unification. Developers need to learn only one platform, Spark, and users can take their apps to everywhere. So, for example, by using Spark, you can interact directly with NoSQL databases. You can interact with Hadoop and HDFS, and you can interact also with the other solution transparently. You just have to learn one tool. You just have to learn Spark, and then you can implement your batch script. You can implement your interactive programs or streaming programs, being able to use different underlying technologies just by using Spark as a middleware. Uh, okay, in this slide, I also mentioned other Spark advantages, but I think that due to the time limitation that we have for this lesson, we can skip. So let's move on the last two topics of this presentation. The first topic is the trusted smart statistics concept. Okay, in order to introduce this concept, we can say that nowadays internet is simply a part of our society, and we are accustomed to deal with digital data every day. Citizens and enterprises increasingly leave behind digital footprints. It's estimated that on average, each person produces about 12 gigabytes of data per day. So the idea is this one. By mining these footprints, it's possible to describe a wide range of socio-economic phenomena in near real time. Most, if not all, data in the course of the third decade of this century is expected to be okay. It's expected to be organic. This means that produced by people's activities, systems, and things, including billions of low-end and affordable smart devices connected to the internet. And in this case, we are talking about the so-called IoT, Internet of Things. In addition, the fourth industrial revolution and the industrial IoT are transforming manufacturing operations, bringing smart technologies in the spotlight and automation to a higher level of integration of smart systems. So the IoT, the Internet of Things, has the potential to offer added value to the production of official statistics. Statisticians like us have a new opportunity to produce official statistics that use an extended IoT data ecosystem. Smart statistics can be seen as the future extended role of official statistics in a world impregnated with smart technologies. And smart technologies involve real-time, automated, interactive technologies that optimize the physical operation of appliances and consumer devices. Statistics themselves would then be transformed into a smart technology embedded in smart systems that would transform data to information. So, trusted smart statistics can be seen as a service provided by smart systems, embedding auditable and transparent data life cycles, ensuring the validity and accuracy of the outputs, respecting data subjects' privacy and protecting confidentiality. So as you can see in the image that I provided in this slide, the trusted smart statistics are a portion of the statistic production, and trusted smart statistics are made from data generated by new sources. So we have statistics made from new data sources, and the most important thing is that these new data sources are different from the traditional data sources, such as administrative registers or survey data, because the new data sources, such as data coming from sensors, data coming from social media, data coming from uh, Internet of Things devices are produced automatically. You don't have to ask data, you don't have to ask information to an entity, to a person. You can basically collect all this data autonomously. So in a silent mode, passively, you just have to listen. You just have to collect these data that are already available. You don't have to ask for them. So that this is the trusted smart statistic concept. Of course, on the base of this concept, you can find several initiatives. For example, the web intelligence, the trusted smart surveys, and so on. And there are already some projects that are going on. So, for example, there are projects at European level about smart meters or about land covering, about the tracking of sheep, or about the analysis of enterprises' websites. So all these cases are good examples of smart statistics that are based on new sources, new data sources. And okay, we are almost arrived. Let's talk about the last point in of this lesson. The European Union Big Data Test Infrastructure. The so-called BDTI is one of the three latest additions to the European Commission's Connecting Europe facility building blocks, together with another project called the Context Broker and e-archiving, another project. BDTI aims to help European public administrations explore new ways of leveraging the potential of their data assets so that they can improve their policy making and provide the best possible public services to their citizens. The big data test infrastructure was born to enhance the building of a competitive data and knowledge economy in the European member states. It basically offers as a platform big data tools, knowledge, and practical support for public administrations to be able to pinpoint areas that need attention and transform, therefore, the way they serve the society. The big data test infrastructure provides a ready-to-use cloud-based test infrastructure that enables experimentation with data analytics and the visualization of its results, offering public administrations in Europe the possibility, the opportunity to increase the adoption of big data technologies and the acquisition of analytic skills. So the testing environment, this environment will be complemented by a catalog in the future, of course, of software tools that will help analyze the available data sets. And the big data testing infrastructures also promotes the sharing of public sector data and facilitate the combination of the relevant data with open government data by providing a data catalog with built-in APIs for data ingestion from different data sources. Users will also have the opportunity to join the community, building an innovation portal that will allow them to share best practices, lessons learned, methodologies, and the results of their pilots. So if you want to, just a moment. Okay, if you want to learn more about the BDTA, you can visit the following website, the last one in particular. And if you want to know something more about trusted smart statistics, I also provided a link to a web page instead for the previous topics, in particular for Hadoop and for some theory about distributed file systems or distributed systems in general. You can refer to this book, Distributed Systems, Principles and Paradigms. I don't know if they are already available for free on internet, but you can have a look at them for free, and maybe you can buy them later. So that's all from my side, and I want to thank you for your attention, and I'm sorry for being a little bit late, 3 minutes more than expected. I read a question before made by Gosia. Hello, we also use Impala. What's the difference between Hive and Impala? Which one would you recommend depending on the type of the analysis? Well, of course, for a particular need, you can use different tools. You can use, let's say, Impala, you can use Pig, you can use Hive, you can use Spark SQL in particular. The most suitable solution is based on the needs that you have. So, for example, generally speaking, if you are a programmer and if you want to experiment several stuff, if you want to produce batch jobs or other kind of experiment, usually you should use Pig. If you want to deal with SQL, if you are an SQL expert, you should use Hive. If you want to deal with streaming stuff, you should use Spark SQL. So basically, it depends from your needs. I don't know very well Impala, but generally speaking, the advice that I can provide is that you should read carefully the use cases within which is best to use one tool instead of another. Are there any other questions, comments? Otherwise, I think that we can stop this lesson. Okay, it seems that it's enough, also for you. Thank you again for your participation and for your attention. And I hope to see you in a next occasion, maybe.